So, the next few steps. Now, once you have the forces, define geometry of the walls and the properties of the material itself, you select your trial UFPs, like the diameter and the grade, right? And the number of bolts that will connect the UFPs to the wall. Select your trial post-tension rods, diameter and the grade again. Select drift ratio of interest. So what is your drift ratio? 3% or 4% depending on your performance target. You assume a contact length for each panel. That'll determine your compressive forces and help you with the force balance equation. Assume moment resisted by each panel. And then perform design checks and accept specified coupled shear wall system. And if it doesn't work, then you have to reiterate and choose a different geometry and a different trial panels. So when we carried out this proposed design, this is what we came up with. One VLT panel, the other panel in the middle, they have U-shaped flexure plates. These plates are welded to these larger steel plates, which are then using long screws, inclined screws, because you need purchase on both directions. If this is moving in this direction, one set of screws are engaging. If this is moving in this direction, the other set of screws are engaging. And this is then done along the whole length of the wall, which is 28 meters, which is roughly 28 feet, which is roughly divided by 3.3, you'll get the height of the wall in itself. So these are some grades, and these are all imperial units. We still use imperial units in the US. Double dash is inches, feet. So almost 8.5 inches thick panel, 4 feet wide, 30 feet tall. 30 feet is roughly 10 meters. The grade is A572, ASTM A572 grade steel. UFPs, these are the specification of the UFPs. And then the post-tensioning rods were a high grade, a BD strength rod, which is way higher grade than any other. A lot of steels out there, 1.5 inch diameter. And this is your post-tensioning ratio. The rods were initially post-tensioned to 93% of the yield value, which is quite a bit higher. And that happened because what happened was this building was designed for Seattle, which has high seismicity. And this phase was an added phase on the testing. Initially, we did 2 different phases, one with buckling restraint brace frames, or buckling restraint braces and energy dissipator. And the other one was with the U-shaped flexure plate, but with one wide panel with bounding columns. So this was an afterthought, and to fit everything within that geometrical constraint, I'll show you some pictures and videos, we have to have a very high post-tensioning force. Generally, it is recommended not to be in that level. Generally, 60 to 70% of the yield is fine, because then there is a danger that you can yield the rods while post-tensioning rather than when the actual motion were happening. Most of the other researchers generally yielded to about 40 to 50% of the yield value. This is what the building looks like in elevation. So you have your columns, which were also timber, your floor diaphragms, which were also similar product, but larger dimensions. And this was the wall system that was installed. 3-story tall building. The post-tensioning cable rested on a saddle. You use divided jacks to post-tension. Remember, Datta sir showed you a video of the testing here with actuators. And generally, what you have your mode shapes, right? You did some eigenvalue calculations. How did your first mode chip look? Did it look something like this? Did it look something like this? So it's pretty much a linear distribution of your first mode. So that's what we assume, that we'll have a first mode distribution. If you've done some experiments below in the lab, you'll know that these experiments are displacement controlled. Essentially, the actuator is displacing the building. Because of the stiffness, a force is generated, and that is measured by the load cell in the actuator. Our first the roof actuator was our main actuator. We call it our primary actuator. The other two actuators at the two different story heights are called the secondary actuator. So the primary actuator was displacement control, so we can control how much displacement we want to give. And then based on the mode shapes, well, first with the displacement, it will give you a load reading. And then based on the mode shapes, you are doing the second and the third as force controlled, based on this ratio over here. So again, it's a very synchronized motion that we use for testing. Any questions? Few more things. As I said, these are some LVL and MPP are different kind of timber products that we used. As I said previously, that it's a decoupled system. Your lateral force assessment system is totally different from your gravity system, with one point of interaction where the diaphragms transfers the load into the shear wall. And that's done at each floor level right here and at the base as well. And essentially it's a steel bar that goes in and out of the plane of the screen and is welded to the floor with some steel plate, which is bolted to the timber floor. Maybe I have a picture. And that bar, because of its stiffness, transfers the load between the diaphragms and the shear wall. Again, there is no gravity loads that are coming into the shear wall, and that's one of the requirements of this kind of a decoupled lateral and gravity frame system. So this is the saddle at the top. There are two post-tensioning cable for each panel, and each of these post-tensioning cable, we hooked up a jack to it and post-tensioned to that 93% of yield on either side. You see this plate, and there is a steel bar going in and out of this plate here, and that's what's transferring at each floor level the lateral forces. We also have grids here for visual observation. These grids are 25 millimeters by 25 millimeters square grid. We wanted to, after each stage, after 1% drift, after 2% drift, we stopped the test and did some damage assessment and then continued the test after that. The loading protocol is what we call reverse cyclic pseudodynamic loading. So very slowly, you'll go back and forth on the building, then increase the amplitude a little bit, then again go 3 cycles, then increase the amplitude, then go 3 cycles, then increase the amplitude, so on and so forth, until the 4% drift is reached. So after each main cycle, there are 2 trailing cycles. So you have a main cycle of a large amplitude right here, and then you have 2 trailing cycles, just to see the hysteretic and low cycle fatigue effects on the connections itself. Have you studied low cycle fatigue in your undergrad?
Constant velocity or
With constant displacement rate, yes. This protocol was developed by this institution called Curie. It is a consortium of universities for research in earthquake engineering. After the 1994 Northridge earthquake, this was formed, and they came up with a lot of different protocols, guidelines, recommendation, and one of their recommendation was to test structures going forward using this kind of a protocol. There are 3 different types of Curie protocol, and this is the one which is quite widely used. So there's a beam and column, then you have this load transfer beam is connected to the actuator. Essentially, that's what's transferring the load from the actuator to the floor system. You have the UFPs here, you have the couplers. So rods have limited length, right? So you cannot get a 28 or 30 feet long rod. You get 12 feet long rod or 15 feet long rod. And then you couple them using couplers. So these are the couplers here. That's your diaphragm system. And then you have a loading bar here. One unique thing, because this is not a dynamic test, this is not on a shake table. And we're going back and forth very slowly. As I said, one is the leading panel and one is the trailing panel or the following panel. But to engage them, you need a tying system. And that was achieved by, again, rods and plates at the end. Questions? This is the position of the bar. This is the position of the bar I was talking about, the steel bar that was welded to this plate. It's not very visible in the pictures, but it's welded here and welded on the other side. And that's stationary, and that bar transfers the load in between the shear wall. And this is the shape of the bar. It was a big experiment, 3-story tall building, right? So we had more than 100 sensors. That meant we needed 3 data acquisition systems with roughly 36 channels each. Do you know what data acquisition systems are? DAC? How many of you have done experimental work? Raise your hand. Done in the lab? Okay. So to measure anything, you have to use an instrument, right? It could be strain gauges, it could be spring potentiometers, it could be LVDTs. Those are all voltage connected. Then they all go into a DAC, data acquisition system. This is the backside of the DAC with all the cables. 100 sensors. So we had, as I said, spring potentiometers, some cheap LVDTs, some spring-loaded expensive LVDTs, load cell, strain gauges. They all are giving you different kind of measurements, right? Spring potentiometer gives you displacement, relative displacement, so does LVDTs. Strain gauges gives you strain, load cells, load. All incorporated in there. So this was our only chance to measure pretty much everything. So you'll see roughly 11 or 13 LVDTs across the bottom of the wall. We wanted to capture the uplift. We wanted to kind of get an idea of plastic hinge length, which we couldn't, but we wanted to see where it fails, what's the uplift, and what is the behavior. The neutral axis lies while it's rocking back and forth, and what is the behavior. There's all the LVDTs are here, strain gauges on the post-tension cables, some string potentiometer for global displacement at the top of the building, and so on. Again, all this data, along with raw data and process data, is in this database called NSF is National Science Foundation. It's a federal organization, so anything that NSF does, it's free. You can go to this design safe database. You have to create a login, and then you can access Not only this data, but most of the experiments that I'll show you today, and even the ones that have been done previously, under the NSF banner, they're all uploaded in Design Safe. And those data you can use to calibrate, build your model, calibrate your model, and maybe verify your model. So if you're doing enhanced modeling, that's one of the ways to really make robust data, or really make robust models using some good experimental data. Here's the building. This is a time lapse. This test took 2 days to do. So this is a shear wall, one of the L-shaped shear wall, one portion of it. The actuators are connected here, 1, 2, 3, and then there's a staircase that goes up and down, but the building will move back and forth. Pretty similar to the lab downstairs, but this is designed only for timber, so your reaction wall is a little thin. And then you'll see towards the end of the test, because we went back and forth slowly, you'll see a lot of displacement. So keep an eye out of this straight column which was detached from the building, and then you can see the relative displacement. So we took the building to 4% drift. So for 30-meter tall building, 4% drift is 1.2 meters. That direction as well as that direction. Shrimali said this is the video of our lab. So I'll start the video, but this is again reaction wall, 3 actuators, and the timber test. Again, going very slowly back and forth for our quasi-static cyclic loading. And as I said, the top of the roof is a 1.3 meter displacement or drift.
How much drift is?
1.3 meters. Let me play that again, just for, again, because it was going very slow, it was a quasi-static test, not a dynamic test. And after like 1% drift, we stopped. We took pictures, did damage assessment. After 2% drift, we stopped, and so on. So we took our time getting as much quantitative as well as qualitative data we could get from this test. Because these tests, as Shrimali sir will tell you, are very expensive to conduct.
Capacity of actuate. Capacity of actuate.
All right. The reason I'm laughing, I'll give you an.
50 lakh rupees. I don't know US how much it is.
Sorry, what was it, sir?
India it costs around 50 lakh rupees.
For the actuator?
The cost of the test.
Cost of the test. Yeah, I can tell you the total cost of the project, which is a little inflated, but this is 300 kips, so 300,000 pounds. 1 pound is, Google it.
85.
So 300,000 pounds, 100,000 pound, 100,000 pound. We have another one which you probably cannot see. It's resting on top of the reaction wall over there, which is 600 kips. 600,000 pounds.
It's nearly 100. 100.
100 Newton? No, more than that, sir. Let's see. So 1 kip is 4,000, roughly 4,500 newtons.
112.
So 1 kip is 4,500 newtons, so 600 times 4.5 newtons, which is so This is our structural response. For that, again, the tests are in the gray. This is our bilinear model. That's the backbone. Day before yesterday, Datta talked about backbone. What is a backbone is? It's a hysteresis, backbone curve. Again, story drift ratio. If you read any earthquake engineering paper, you'll find this chart over here. What is our drift ratios? We did that. We did see a soft story mechanism when our building was not connected to a shear wall. We tested that just for fun. We saw a soft story mechanism. Now these connections are specially designed by a company to go to 3.5% drift. So I talked about drift compatibility. Simpson Strongta is the company. They also have a presence in India. They have an office in Bombay. They are pretty much the market leader for timber connections, but they are also into concrete and other things. And this is a structural response with the shear wall attached. And our mu we calculated as 5.69, so roughly 5.7. Our R was 0.123, so not a bad design for what we are trying to achieve. We wanted this mu to be higher, 12 or 13%, but 12 or 13, but with wood, that's what we can get. Again, story drift ratio versus floor level charts. I'll not bore you with a lot of data, but this is what it is. This is our design curve versus this is our performance curve. So our performance curve is a little bit higher than the design curve. And this is with our shear walls in there. So this is the wall in close-up. The video shows what from 1 to 2% drift ratio, and I think this video does not work, but we'll go to the next one. Oh, this is working. So from 1% roof drift ratio to 2%, the video, it's not a lot of displacement at the base of the wall, but you can still see some. It's moving a little. But from 2 to 4% drift, I think you will see a lot of action at the base of the wall. So you can see how the wall is moving up, decompression, and localized compression after that. And you can see the UFPs also opening and closing right here at the end. So that was your localized compression. This was a damage assessment. You go to another primary cycle, which you have more damage, accumulated damage at the base of the wall. This is like at about 4%, a lot of compression, localized compression.
So only if we focus on the cross, like L and we can provide some strengthening measures, so we can even achieve that 4%.
Yes, so there are compression shoes that you can add steel in there, or you can have fiber reinforcement, and then you can strengthen them. So yeah, good question, good idea. And people are doing those kind of things as well, yes. From 3 to 4% roof drift ratio on the other side of the wall now. And you'll see it's not as dramatic as the other one, but it's still, because the other one has already crushed, if you can see here. So that side crushed early than this side. And that happens because of the stiffness of your fixturing, because there is inherent stiffness of the fixturing, so there is a little slack in the system. So our residual drifts after different cycles. So after 4%, our residual drift was on one direction less than 1%. In the other direction, because it compressed, you saw that compression, and there was very high localized buckling of the shear wall, our residual drift after 4% was little less than 1.5% in the positive direction. But our design objective was after MCER, after 3% roof drift ratio, our residual drift should be less than 1%, and we met that. So on both directions, our residual drift is just a shade below 1, and this is way below 1. So one of the design objectives were met, but we wanted to check it at 4% as well, which did not meet on one direction. And then we did a lot of visual observation and visual characterization to see the damage propagation as well. And there were damages, localized damages here, localized damages on the profile. As we go along, there's localized damage there. More damages as we go to 4% roof drift ratio. So yeah, we have a lot of documentation and damages of pictures of damages that we can build a story and tell a story around. Again, this shows the panel uplift on different directions. The north panel, the south panel with pushing and pulling. And you can see there's a slight difference in the behavior. In an ideal world, these should be similar, but there's a slight difference, and that difference is because of the slack. So you have steel connecting to wood through LVL beams and some angle brackets for your force transferring mechanism. Every screw, every bolt has some slack, some tolerance. And that tolerance, when you multiply over the whole length of the building, it's exacerbated in one direction and less in the other direction. So that's why you're seeing the difference. Otherwise, the behavior should, in an ideal world, in your models, the behavior should be similar. UFP visual observation, you can see some milling here at 4%. This is initial, nothing, no damages, but here you can see some turning, yielding, and scale milling of the steel. And post 4%, you can see more damages and opening of the UFPs or U-shaped flexure plates. Questions? Close-up of that, you can see a lot of, this is applied lime wash. So you see a lot of lime wash is flaked out because of all the movement, and you can see some localized damages here. So this was the conclusions from the test. I won't bore you with those, but generally our design criteria were met, and we did a lot of validation. So we did experimental validation. We could also have done a numerical validation, but we need experimental data to build our numerical models, to calibrate our numerical models. So this is one of the tests that helped us do that. So essentially, we developed a design procedure, developed and carried out an experimental program. We provided recommendation based on testing and design, and create a standardized format for data availability, and also we identified limitations and all. So this was part of that project in general. But what I want to leave you with is a few things. So the first is there has been a lot of things going on in the performance-based design field for timber engineering. So there is a shake table, a real shake table in San Diego, University of California, San Diego. It's an outdoor shake table. It was a unidirectional shake table initially, but now they have upgraded it to a 6 degrees of freedom shake table. So it can go this, this, and this. So in 2017, we tested a 2-story mass timber building with timber concrete diaphragms. So timber topped with 2 inches, so 50 millimeters to 75 millimeters thick concrete topping, converted with screw and attached with screws. Well, there was screws as reinforcement, and then the concrete was poured on top of timber. That was one of the projects that we did, and that work led to a lot of different code changes on the timber concrete diaphragm and design guides for that. This is a 10-story project that was conducted in 23 and 24, mainly in 23. Here you have different timber floors, and this is after the upgrade to the shake table. You have 2 shear walls of the same material, which was VLT kind of material, and the other one was CLT, cross-laminated timber on these 2 directions. We needed 2 direction. In this one, you'll notice there's only shear wall in 1 direction, because this was at the time when the shake table was unidirectional. Now, with 6 degrees of freedom, you need a bidirectional lateral force resistance system. Then what we did was, this was a project done by one of our colleagues from a different university. Then we at Oregon State University took over this project. We took out top 4 stories, discarded that, and then we had a 6-story building that we tested for multiple ground motions. And the way it's linked, because this is what we did in our lab, and we tested 3 different lateral force resisting systems. In here, the best performing 2 was tested on the shake table with the 6-story solution. Now, why is this needed? Because we are trying to codify and learn new things with this system. This is a new system. Still, codes are very conservative, or structural engineering community is very conservative in general. So we needed more data. But why do we need to test similar systems at different level? 2 and 3-story is kind of the low-rise segment. Then you go to a tall building segment, which is the high-rise segment, 10-story. But you have nothing, you don't have any data for mid-rise. So that's why we needed a data point at 6, which gives you mid-rise. Now you have covered low-rise, mid-rise, high-rise, and you can draw whatever conclusions you want to from there. The other thing, there are subtle differences between the materials. So this was CLT, or cross-laminated timber. You can look it up. It's one of the most promising materials, timber materials that are coming up. So this was all cross-laminated timber. This was all the new material that we developed and used, VLT and mass ply panels. This had amalgamation of all different timber materials available. Same with this. We have completed our tests. We are writing papers. A couple of papers are out already on these tests, but in 25 and 26, you'll see a flurry of papers coming out on this and this. This, we are not directly involved with this, so we are not part of those papers, but the papers are already coming out for these tests. So, the first test that we did was 2017 shake table test, Northridge earthquake ground motion. Sound है क्या? Boss, sound है क्या? So, first 2-story test, it's just better with the sound. It's a Northridge earthquake, 1994, California had an earthquake. things cannot be done alone, so there are a lot of universities involved and a lot of different companies involved in the whole effort. I already showed you the video for the 3-story building, so we'll spare you that. But then, moving on to the 10-story building, there are a couple of really cool performance videos if it works. So, somebody asked me about non-structural elements, and these have non-structural elements that are specially designed for 4% drift. Again, so it's a 10-story video, 10-story tall building. This is the plan view, or using a drone, you capture it from the top, and this is at one of the shear walls at the base. And all the videos are synced together, so let's see if it works. So even after Loma Prieta earthquake at MCE level, there was no damage. Yes.
As I have done on work on non-structural elements, so basically I found that in bottom story we could not found out much more amplification. But as we go on top floor, we found
Dynamic amplification, yes, that's a great point. However, these were all, this is not just the bottom story, but 4 stories tall, non-structural elements were. So this is 4 stories here.
Sir, we have tested only for the cell plate only. The structure is tested only
For this, only for the cell plate, yes.
But sir, there is additional load during the earthquake.
Yes, there are steel plates, there are thick steel plates on every floor.
Okay, sir. Yes, that's why I'm asking.
Shrimali sir, have you seen this one?
Please again.
Sure. This is a 10-story building test, which a few of our colleagues did. So all these systems are based on performance-based design for functional recovery, non-structural elements as well. This was tested for MCE at Loma Prieta. So Loma Prieta was an earthquake. Took the ground motion, scaled it up to the MCE level. And that's,
These are taking Loma Prieta.
so we tested, the video was good. So we tested for like 48 different ground motions, sir. North Ridge,
Ground motion, which is a unit type of earthquake.
yeah.
Large displacement is coming.
And that's what we wanted also. Our favorite go-to is the Northridge earthquake. That's what we do a lot. Then we also did Mexico City, Tohoku, but we tested like 45 to 48 different ground motions at different levels. So it was just a suite of ground motions. And then we took over the test. We did a 6-story. We replaced the shear wall system, put new shear wall system, and did a 6-story, and also did a lot of different tests. So this is one of the UFPs, rocking wall system. This does not have.
This is going to be pretty dramatic.
But this is Simpson strong tie healing system, so it's a hybrid building with steel and wood. For the 6 stories test.
One more to go.
So this is again in UC San Diego. These tests cannot be done alone, as I said. So this was essentially a public-private partnership. We got funding from the federal government, we got funding from the state government, we got funding from industry partners. So Simpson Strong Tie was one of the industry partners that helped us do this test also. I'm not sure why the previous video did not work, but let's see if it works. So this is the one previously to switching out to a different lateral system. It still have the UFPs, so this is a close-up of the UFP walls while the shake table is shaking. And after that, we took this wall out and put that steel air-link connection that we saw in the previous video. In total, this building went through 130 different ground motions at different levels. So roughly 45 or 25,000 years worth of earthquakes. Again, I'll leave that. So that's pretty much it. Questions?
What kind of connections were given?
Connections? Essentially, those are steel connections made out of steel. Since Simpson was involved, they are one of the market leaders of connection. So some of the connections were custom designed by them for withstanding that much drift, 3 to 4%, and then withstanding low cycle fatigue, because the same gravity connections are going through the 10-story test as well as the 6-story test. So the bottom 6 stories, they're going through like 300 different ground motions. So they did a lot of research and development and came up with the best type of material and the connections. So the beam to column connections were designed for drift compatibility, and that is a connection that's not in the market, and they are still doing research on that, but they did it specifically for the test. Any other questions? So now you can all design a building with PBD. You might have gotten 2 different papers. One is a PBD or DDBD for steel frame. The other one is on functional recovery. So please read them in your leisure, and that'll give you some insights on how it's used in general practice.